good afternoon everyone. Sorry about the delay and little technical glitch. Welcome everyone to this 11th seminar, the series of talks we've been holding under the research initiative for geophysical flow lab. It's my pleasure to introduce Professor Sutanu Sarkar from the University of California at San Diego. He is with us, he's been here with us since yesterday. We're going to talk to us on stratified gates. The brief bio about them, he received his PhD from the Mechanical and Aerospace Engineering Department at Cornell University in 1988. After 4 years as a staff scientist at the NASA Langley Research Center, he joined UCSD, where he is currently the Blasker Professor of Engineering. His honors include the NASA Group Achievement Award, the Friedrich Wilhelm Wessel Research Prize from the Humboldt Foundation, Fellow of the American Physical Society, Associate Fellow of the American Institute of Aeronautics and Astronautics, and Fellow of the American Society of Mechanical Engineers. And he is currently a professor in the Mechanical and Aerospace Engineering University.
Thank you very much. I appreciate the invitation, and sorry to keep people waiting, but I don't have too many slides, so that's a good news. So I'll try to keep it short. So I'll be talking about stratified gates, and primarily we'll be talking about topographic gates, and this is work done with Sutanu, Dino Pollard, and now the one view. And I worked for a number of years on engineered structure gates, so I won't have the time to really talk about that particular work. And there are similarities and also big differences in these. So this is Pranav, who has now graduated with PhD and making good money. Dino Pollard is my colleague, and Jinuan is doing PhD. So geophysical gates, so some examples are here. So these are actually mountain gates. So and you can visualize that using the cloud cover with the natural visualization tool. And you see these armor vortices that are swirling around. They're very large vortices. And then on a smaller scale, you will have these sub-little scale vortices. Sub-little scale is between the mesoscale, and mesoscale is the essentially rotation is very tall. So the radius of the eddies is larger than what we call the first deformation radius. And then here even E2, E4 are 4 different vortices there. Maybe we can turn off the light perhaps for the presentation or different. And then here we have the tidal eddy dipole. So I'll be talking about tides quite a bit. And when you have tides which go back and forth, and these are island waves that are coming off, in this case, the Holland Island group, and you see this nice dipole being shed on the island. Then, of course, we have the weights of engineered structures. And the weights of, and here stratification matters because, and I'll talk about what exactly is going to do in stratification, basically density stratification. So the ocean or the atmosphere. So you have a density gradient so that the stable configuration of flows is that maybe below light. And you have these examples in here. So this is like this underwater permissible used for exploration, really. And then here you have this wind turbine wave, and then you have these different vortices that are being shed from the blades, and you have the spiral vortex pattern. This is a sort of obligated image that we're talking about wind energy, which is big wind farm. And now you have a whole collection of these blades. And this is a simulation that my former student Jose did. So this is a prorate spheroid, so it's a long, slender body. And then you have the wave coming out of this highly filled and so on. So here stratification matters because eventually what happens is that although the speed may be large and the relative effect of buoyancy may be low, what happens is eventually the time scale of the flow becomes small enough, it becomes comparable to what we call the buoyancy time scale. And the buoyancy time scale basically increases as the stratification does, dρ by dc. We're talking about a vertical gradient. So, and also if you look at submerged waves, and then this is like this is so-called Luzon strait. So it's like two-dimensional topography on the large. So you've got two parallel long ridges, but interspersed between them, you've got these little hills and bumps and so on. And then these are three-dimensional objects. And these are underwater mountains. So they are way below. So just like you've got your hills and mountains you see in nature outside, then these are hidden, they're submerged. But then what happens is that you have these flows and eddies that are generated. And then the question is that what is the eddy structure, what do they do, and so on. And geophysical turbulence, when we talk about geophysical turbulence, so there are two basic differences that your nature stays with us. One is the density stratification that I talked about. So here you have the density gradient, so you have eddy, right? And the density gradient is proportional to a quantity called n squared. And n has units of 1%. So n is a frequency. It's a natural frequency of the stratified. So natural frequency gradient. And then similarly, you have Earth's rotation, and then you have omega, which is your rotation rate, and that is 2 pi times fc. Okay, so then you have two new dynamical parameters, n squared and your Coriolis fc, and those in affect the fluid mechanical elements that we all know about. So like what vortices, boundaries, and so on. And another thing is that since I said that n is a natural frequency of the medium, what that means is that if you have any perturbations to that medium, then they can be carried by the medium with a buoyancy frequency which can be as large as n. And in a non-rotating fluid, it can be as low as But F, in a rotating system, F is a lower cutoff of the frequency. Frequencies between F and N are small. So my background is CFD, so I'm a mechanical analysis in my training. So what I'll be talking about is the tools that we learned from CFD and how could we apply them to these geophysical problems and perhaps learn something from these applications. So I'll be talking about 3D topography. So one thing I want to make clear is that the 2D topography is quite different from 3D topography in the following sense that if you have, so what stratification does is that it sort of, it does not, it restrains vertical motion. So a fluid particle that's coming towards your hill, right? Now, if it doesn't have enough kinetic energy to combat the potential energy barrier to the stratification, it need not go up, it can go around. So if you have 3D, then you can go flow around and therefore you can have eddies. So that is a big qualitative difference. The other qualitative difference is that because now fluid can now go around rather than going up, the internal gravity waves that are emitted become less important. So for internal gravity waves, you must have some vertical component of motion. That then the points is restoring force, vertical. So indeed that vertical component. So there are two things that happen. So here I'll be talking about tides, and I'm going to show you an example where the tide happens. So So you have, so this is the so-called green island wave. So the green island is a small island of the mainland of Taiwan. And you have a current that's going, it's pretty strong, it's about a meter per second. But then you have the tide that goes back and forth. And we all know about water shedding, right? So you have a body, there's a screw hall number associated with the water shedding. So now the question is that if you have these vortices, right, what should the tidal stream be? And then when they made measurements, what they found was that the spectra, so these are mass spectral density, and they took the mass spectral density at different stations in here, and W1 and W2, I guess this is W1 and W2, and this is of the streamlined current. And what they found was that they had peaks at M2. M2 is a diagonal, semi-diagonal tide. It has a period of 12.4 hours. And then K1, which is like a diagonal frequency, and then you have M4, which is the higher frequency. So these two tidal constituents had the peak. So then the question was that, okay, so and they're seeing vortices, but these vortices have the tidal frequency. So I said, okay, let's take a look at under what conditions do you have the natural water shedding frequency, and why does it go to something that is very related to the tidal frequency.
Sorry, I have a little question. How many tides are governed by phase of the moon?
It is, yeah.
How does it influence this?
So what happens is, depending on the phase of the moon, you can have a stronger tide or a weaker tide. So the amplitude changes, but not the frequency.
What rates is this being had?
In this particular case, what generates this current itself? So the current, oceanic current. Yeah. So this is actually this is last stage current that is there over a long time.
What is that box, green box, and usually the bodies and
Oh, this green box is showing a difference between the two particular stations, W1 and W2, but that's specific to that paper. That's not included. So what are the questions regarding peaks of molecules? One is that how you have a current that separates off the island, and then you have an oscillation. So how do the tides affect those separations? What is the role of the tidal separation on vortex dynamics and form track? There is turbulence. We are interested in oceanic turbulence. So turbulent dissipation. So in this particular flow, where do you have strong turbulence that drives ocean mixing? Effect of rotation is ongoing. I'll talk a little bit about it towards the end. And there are observations and lab experiments at low density number. And there have also been observations of topographic break. For the most part, they have been hydrostatic. And also, most of the previous work of breaks have been without tides. So we've been looking at this problem using so-called non-hydrostatic turbulence resolving simulations. So hydrostatic is without getting into details about it, it's a very popular tool in large-scale ocean modeling. So that allows you to solve more computationally in a more efficient way for the pressure case, essentially. So essentially what happens is that the vertical velocity equation, so you simplify it so that there is basically you drop the acceleration of the vertical velocity. And in fact, I'll do another video more. So if you look at the model problem in here, so I have a pole, my conical hill, height h, diameter d, there's a current uc, and there's a tide going back and forth uc amplitude, and its frequency is f sub T. These are your dimensional parameters. I told you about n squared, which is the buoyancy frequency. So we'll be looking specifically for this part of the talk in weak rotation. And when we say weak rotation, what do we mean? What we mean is that the inverse time scale, dc over t of the flow, is much larger than the inverse time scale associated with rotation. Okay? Strong stratification. So the fruit number is not like super small, but it's less than order 1. So some of the flow will go over the topography toward the top of the hill, but most of the flow is going to go around. So the first thing is that if you have a situation that's unstratified, there is no stratification, everything else remaining the same, then what happens is that you do not see these nice coherent vortices that we just used. I showed you the difference between vortices. Because if you have a high density of flow over a hill, then what happens is that you get, at low density number, you get some sort of coherent structures. But those are active vortices. Those are not your eddies with the vertical axis. So you need stratification to see what is it that you're talking about. Okay, so here's the conceptual model. So you've got the tide going back and forth, and let's take just one horizontal plane for illustration. And so you have vortices that are going to be coming out, separating from there with the negative side, vortices to the positive side. I'm going to take R, which is UT over UC, UT being the tidal velocity amplitude divided by UC. I'm going to take it to be 1. And that makes us crucial simplification, because now I'm not going to have vortices on the other side. Right? So by taking R equal to 1. So that is all. When I say lead vortices, leaving the back of the object, there's one back of the flow rather than 2 backs. And the excursion number is basically what it is so UT by 2 pi ft is the excursion, the distance traveled by a particle over one time period. So I'm going to compare that with T. So if your excursion number is very small, then all that the particle is doing like so. It doesn't really contribute. Doesn't seem to work. Okay, so weights. So we see weights and internal gravity weights. Let me show you the internal gravity weights. And we're talking mainly about weights, but it's a nice picture. So these are isopycnals. It's strongly stratified. So these isopycnals, and there's no horizontal density gradient. So you have straight, they're not inclined, they're parallel to the ground, isopycnals. There are small perturbations to these isopycnals of constant density lines, and these have a certain relationship in phase, and those correspond to what we call transient V waves that are taking energy away from the flow and releasing it out to the field. And then here you have the weight, the vertical cross section of the weight. You see lots of fine scale structure in here in velocity. And then if you look at a horizontal cross section, then you see these vortices, and we'll talk more about that. So this is a vertical vorticity, omega z by m. So let's talk about the big vortex frequency. So this was the first part of the main chunk of the thesis. So what we did here is that we kept R equal to constant, and we changed the so-called tidal excursion number by changing only Ft, the tidal frequency. That's what we changed. And of course, if you're looking at in the ocean, the tides are discrete frequency. So it's like, so I'll show what is the dynamical significance of that. So we use an NES non-hydrostatic model. It's pretty highly resolved, but still not DNS. It resolves most of the analytic scales of the turbulence. And it's a pretty large grid. And so if this is the diameter, then you have significant upstream distance and downstream distance and so on, we handle the conical obstacle. This conical obstacle is pretty steep. So h by d is 0.3, but mechanics standard this is very steep. And it's handled with the inverse boundary method that we have developed. And as the Rossby number is 5.5, weak rotation, strong stratification, then some is 20,000, so fairly high. So let's introduce the relative frequency. That's a useful concept. So relative frequency is the ratio of Fs sub c, which is the vortex shedding frequency for a pure current. So that has a small number associated with that. And I'm going to not compare it to the tidal frequency, the oscillation component. And if you do that, then that's F star. And then for this particular configuration, if you use the current with this stratification and do the simulation and conclude the theory, then the Schumann number is 0.26. We'll check that against what's known. And the variation in the tidal excursion number that I talked about is really, you can view it as the variation in this F star. So what we do here is that we will change Ft to change F star. So, and the shedding frequency FSC is the Schumann number, which is some number, in this case 0.26, times UC over T. So that's your regular definition. And you can see that F star is proportional to DHC. So essentially what we are doing here by changing F star, the equivalent in the ocean is that you have a certain hill or a certain topography, and you have a tide with a certain frequency, and you have a multi-scale topography. So if you encounter a hill with a smaller peak, then the vortex shedding frequency F star would increase, right? Because B is decreasing, so F star should increase, Ft because FSC has increased. And so an example is that if you take M2 tide with a period of 12.4 hours, and the U is 0.2 meters a second, and the Schumann is 0.26. So when I change F star from 0.1 to 1, that is equivalent to changing D from 3.7 kilometers to 0.37. So essentially, by changing F star, I'm going to change the size of it. And so let's consider the case with F star equal to 5 over 6. So you have a plane of D star of 0.24, and so this is the vorticity in here. So what you can see is that this vortex path, if you look at it, T equal to 13 T is the same as T equal to 15 T. Similarly, T equal to 14 T looks very similar to 16 T. So here we are getting a periodicity in the flow in time with a period of 2 times T, where T is the tidal period. And so the vortex synchronization, there's not an explanation for this. So if you look at the vortex shedding, then there's a spatio-temporal symmetry, right? It's a Carnot weight. So essentially, uxyt is the same as ux minus yt plus ts by 2. The reason being is that ts is the vortex shedding period. At ts over 2, you have a vortex on the opposite side being shed on the opposite side. So that's just you can see that. And the tidal forcing, you have a body force that's going back and forth, right? So what it's trying to do is that it's trying to impose uxyt is your x minus yt. So x is the distance from the object, y is the distance away from the center line. So this is your symmetry imposed by the tidal forcing, and both of them can be matched when ts by 2 is the same as n times t, which basically means that the tidal the vortex shedding frequency Fs that you see has to be some harmonic. So this is really the reason why the wake synchronizes to us. And these are the results that we get. So you've got fs over ft in here as a function of, so it's like, it's non-dimensional, but let's say that I had a situation where ft was so and fsc was so, then the actual vortex shedding frequency fs that we get, fs by ft, varies. So in regime 2, it is going towards the subharmonic, which is ft over 4, and then it goes to ft over 2. So what's another interesting thing is that the tide is going actually faster than the vortex shedding frequency. But the vortex shedding frequency locks on to a subharmonic. So you have a fast tide which is actually slowing down the vortex shedding that's actually and now I'll talk very briefly about form drag. What we find is that the low pressure is intensified, particularly in the bottom half of the organ. So this is a cross section of the hill, and what we're looking at upstream and downstream. Downstream, you have the coherent vortices, which are low pressure zones. And as you can see that as you change, as you're going from one watershed, one regime to another regime, then this patch of blue that you see, which is the low pressure region, increases. And so because of that, so does the form drag. And the reason is not very difficult to understand. It's basically what's happening is that your vortices are hanging out near the back of the hill for a longer period of time when you are in this tidally synchronized state. And because of that, because of the fact that in regimes 3 and 4, you have these large vortices which are bottom intensified, the mean form drag also increases. So what happens is that the tidal oscillation has zero mean. And so normally what people do is that they take the current and then put a form drag based on the current. But that drag coefficient has to be increased by at least a factor of 2, at least for this particular case. And this is important because really in large scale models, it's the form drag that removes the energy from these currents. We were asking that how are these currents formed? So these currents are formed due to the atmospheric forcing and other the geography of the continents and so on. But once these currents are formed, the energy has to be removed, and that energy is often removed as form drag. And so it's important in the ocean models. Okay, so the conclusion of this particular part is that as I change your F star parameter, which is basically the how fast the tide is relative to the natural vortex shedding, then we go to different scenarios. So if there is no tide, then you see the usual cloud vortex speed. If you have a very fast tide, then what happens is that you get these vortex pulses. They're so fast that they don't really disrupt the tidal frequency very much. But then when your F star becomes between 1/4 and 1/2, then it locks on to this ft over 4 and then ft over 2. And then in this, I didn't really design the paper, but this is the regime in which you get these symmetric dipoles. So I showed you a picture where you had this tidal dipoles coming up, so you see these tidal dipoles during that particular regime. Okay, so in part 2, what we did was that we kept the tidal frequency the same. We kept UC the same, and then we changed UT. So F star was changing, and we changed basically the amplitude of the time. In the first part, we changed the frequency of the time. So that's the proper thing to do.
Can I ask it's been associated with which plane of the bone?
That's a very good question. So, so it's a global frequency. So it's a Schumann number of 0.26 based on the base diameter. So it is not also. So this is a fully three-dimensional carbon vortex field. So if you saw the pictures, you saw that you had these vortices, right? But the size of the vortices changed, but the frequency did not change. So it's a global frequency based on the base diameter. So it's one frequency. So and that frequency does not. We have gone so we have changed the fruit number also. We have not changed the fruit number to be lower than 0.15. So until 0.15, at least we see like a global watershed.
And if I were to associate it with the single plane of the bone,
With the base diameter. It's always the base diameter.
so if I had a two-dimensional simulation with just the base diameter, I would see the same score.
You would see approximately the same. Yeah, it's like a cylinder. Yeah. Yeah, you're right.
I just have a
Sure.
So if this cone was very long, would that frequency be still the same? Because the lower answer
Is changing, yes. So let's assume that the Reynolds number is large enough so that the fact that the local Reynolds, so as you know, for a cylinder, like once the Reynolds number becomes large enough, the sensitivity to the Reynolds number is small. That said, people have done experiments with very tall bones, and there they see actually step changes in the vortex sharing frequency. But there are very few experiments like that. And so, yeah, and well, I mean, since the question has arisen, might as well talk about it. So you could think about a dynamical landscape, which is U over N. So stratification based landscape. And then your food number is basically the inverse of H divided by that particular landscape. And so if that H becomes very large compared to that landscape, which means that your fruit number is becoming very small, then one has to see what happens. If people have done hydrostatic simulations, and they see that even at this fruit number of 0.15, they see changes in the vortex sharing frequency, but we don't. Sure.
One is on slide 19. So there is a dip in the blue. Why is that?
Oh, because what happens is that the frequency, the actual shedding frequency locks onto Ft over 4. But here what we are doing is that your FSC by Ft is changing, right? So therefore it goes like that. So it looks very simple when you look here, but when you plot when you so if you look at the Schumann number in here, right? So the Schumann number is changing in a different way. The Schumann number is normalized by the actual vortex shedding frequency and Q. So two questions. Second one.
In the experiments with tempered cylinders and cavitation, stratified the upstream distance is actually affecting the frequency.
It is. No, sorry, the ups. No, so what happens is that as long as for a three-dimensional object, the upstream distance, as long as it's long enough, you don't have the problem that you have with it's a three-dimensional thing. So if you have like a two-dimensional thing, right? So then it becomes the upstream boundary condition becomes a problem. But if you have a three-dimensional thing, as long as you are long far enough, it's fine. Yes, of course.
There were several studies in the literature like the knowledge of non-stratified fluids, right? So, say flow over roughness limits. So, in there they observe some specific frequency for the kind of geometry studies. So, isolated flow over and isolated roughness element. So, you get to compare what the frequencies you are observing here, stratified fluid, that the typical studies on isolated roughness elements.
Yeah, so the small number of 0.26 that we saw, right, is perfect for a 2D cylinder. So the frequency looks like a 2D cylinder, but if you look at the structure of the flow,
I'm
it
talking
is
about
different.
3D roughness element,
Yeah,
but without stratification.
yeah. So if I take when I say 2D, what I meant is that if you take a cylinder, a long cylinder, so that's 2D in the mean, right? So if you take a flow like so, right, and if you do like a two-dimensional cylinder, two-dimensional simulation of a cylinder, you would get 0.26. But if you do 3D, then it's somewhat different. So it looks like a 2D cylinder.
3D, but it's like without stratification. So
Oh, you mean like a hill?
yeah, like a hill.
Oh, I see. So that looks quite different. Quite different. Absolutely, very different. Sorry, I misunderstood.
The second question is, do you specify any boundary?
Yes. But it's not a super dominant boundary, so it's less than 20,000. So that is a boundary. But the boundary scale relative to the height of the boundary is another dynamical factor. Very small.
Okay, so your boundary is then
Relatively 0.1. So the relative ratio is 0.1.
the third question is like when I looked at some of the body structures, right, to find the cylinder in the wake of the cylinder, you have very finite state. But when you travel the downstream, I don't see that level of unsteadiness. Is it due to physical dissipation or is it due to the chemical dissipation?
Oh, no, it's not numerical. Really careful about that.
Okay.
So there is turbulence, there's dissipation. It's just that the stratified wake, the stratification effect keeps increasing. The local fluid number keeps increasing. So vortex stretching and so on.
Even in the
that.
shape point direction.
Yeah, the local fluid number is changing, right?
Oh.
The wake is increasing. Lateral.
And within one
So-
of shedding like
Not one wavelength. So we got significant turbulence all the way till maybe 5 to 6. Depends on what you call as significant. But 5 to 6 diameters, that's quite a bit of turbulence. Yeah. Sure. Okay. So here what we did was that we oh yeah, I want to show this. So how do I play the movie? So you have to play it in there, I think. And let me go back. Okay, now click. It's just playing, right?
It's not getting
Is content enabled?
it's not playing. I can.
Well, there is some randomness going on here. Sorry about it. It takes some time. So it doesn't matter really, because I'm explaining in words what you would have seen in the movie. And essentially, what I wanted to say in here is that so I'm just looking at a particular ratio UT over UC, which is 0.2, and what we find is that as the flow is decelerating, so you have an adverse pressure gradient. So that adverse pressure gradient is restraining the attraction of the wake eddy downstream. So that's what you see in the movie. And so this physically based on that, what one could do is compare the tidal forcing, which is your dT by dx in from the type. The y is dt by dx, basically d by dt of your time velocity. And you compare it to u dot grad u, where u now is the injection provided for the current. And at some point, the two become comparable dynamically. And what we find is that, and then you take the ratio, you get this time strength parameter, which is the ratio of the two amplitudes, ut by uc, and your excursion of dxt. It turns out that we use an excursion of 0.5. And so the point that S is sufficiently large, you would expect the type to affect the flow. And reviewers asked the first paper, so you've taken R equal to 1. You're a very strong type. So how strong does the type be to see this kind of thing? Very valid question. The question was that is it going to be a sharp transition or is it going to be a smooth transition? Turns out it's a smooth transition, so not that exciting. So essentially what we find is that until R equal to 0.2, the water shedding frequency keeps decreasing until it locks on to the diagonal body. And then it's a very nice and sharp transition to the, and you can see that very nicely here. So if you look at this particular plot, and then you look at omega t over 2, right, there's nothing much going on. And this is the frequency spectrum of the lateral velocity, SVD. But once you go to beyond 0.25, then there is a sharp increase in this water shedding signal. Now let's move on to dissipation hotspots. So I myself am a turbulence guy, so I'm very interested in and in the ocean, it's a rotating stratified medium, so it's not easy to get it to be turbulent. And so that's why there's a lot of the effort trying to figure out where is it that you get strong turbulence. And so these are plots of dissipation, turbulent dissipation rate, and these are plots of the vertical dissipation. So and epsilon star is epsilon divided by UC cube over D. So usually in the statistical distribution. And you see that there's relatively strong dissipation. So you've got like order 1 values of epsilon star, but not everywhere. So a lot of fine scale turbulence and strong dissipation in the near way. And then it slowly decreases. So by 4, even at 4 downstream distances, you have some dissipation, would be your question. And so looking more carefully at the dissipation of hotspots, if you look at the flow, so since it's like a hydraulically blocked flow upstream, so the flow here is blocked, and so you have a flow right in the crest is accelerated. And then that flow accelerates and then plunges down. These are isopicals. And these isopicals rebound. And then you see these V waves that have a certain pattern to them. And they're very related to these bumps that you see in here. So you have a so-called descending jet, and then you have these V waves. So that is an intense spot of intense turbulence. Also, but that's just at the top. Right? The jet goes only so far. But then at the bottom also you have strong strips of displacement. So the flow is separating out in strips that are of the order of UC over N. That's the vertical density. And you get strong vertical shears in that particular So we did so the very interest in the oceanography community is that how much energy is being radiated out from these mountain generated waves. The reason is that all the energy that's going out would presumably bring to give you turbulence and mixing outside. So most people have looked at topography really in the context of internal gravity waves. But then there are some of us who have also been looking at internal waves and these wakes together when you have 3 dimensional topography. So it turns out that the first thing is that the internal wave flux, if you normalize it by the no time case, so you just have a current, no time. So there you have only your steady waves. And if you have the time going back and forth, you have the so-called transient waves. So then you have, so we came with a little scaling there and there. So this is your data from the simulations, and this is your scaling. That shows that the internal wave flux normalized by the no tide case increases dramatically, actually, as the tide, the tide amplitude increases. But nevertheless, the radiated wave flux normalized by the dissipation in the wave itself, the local dissipation of the wave, remains very small, 5% or so. So for these three, so let's say what it's saying that these kinds of 3D topography with a very isotropic topography, right? The cross sections in the circle are not very efficient radiators compared to stirrers, this type of topography. Okay. So these are my conclusions. So I talked a little bit about the time synchronization. I showed you and I explained why there's time synchronization. So the shedding frequency changes in response to the tide, and the other things that happen like the form drag increases and also the wave dissipation changes. So now, again, what we're doing right now is we're looking at the effect of rotation. So this is an ongoing work by Sutanu. And so here now, the fruit up I talked about quite a bit. So this is U and H. Now another thing is that U over D you can think about as like a horizontal length scale of the flow, U over D. And you normalize, these U over D is because of the horizontal distance, you get a time scale, inverse time scale, and you compare that with H. So that's the Rossby number. And generally, a Rossby number is much smaller than 1, as is true for these large vortices that you see under the maps and so on. Then effective rotation really dominates. But if you have a rotating stratified fluid, then one way of estimating the strength of rotation with respect to stratification is to take the so-called Berger number, which is Rossby number, the fruit number squared, which is this guy in here. And if the Berger number is order 1, it turns out that Rossby fruit rotation and stratification are both important. And that's kind of an interesting thing to kind of look at. So what we do is we change F holding all others constant. In general, we don't want to change the topography very much because those of you who do CFD know that the moment you change, and maybe even EFD know, that the moment you change the topography, then you get the kind of stable species. Easy. That point here. Is the battery off?
No, the slight lag.
Yeah. I just don't know. So let's play play this movie.
So,
Okay.
I think it has to be from here.
Yes, it should show here. You should see should see a cursor if you
Can you breathe it separately?
see. I'm not familiar with the PC. Well, that's a pity. But so if you saw the still shots give a good idea, I think. So let's just do that. So this is Berger number of 0.15. Sorry, no, this is quite wrong. So Rossby number is 0.15, Berger number is 1. The Rossby number is 0.75, Berger number is 25. And then the Rossby number is infinity, so there's no rotation, Berger number is infinity. So here we're plotting vertical snapshots and horizontal snapshots for vertical systems. So when you have a strong rotation regime, then you get these sort of cylindrical vortices coming up. So the horizontal cross section in a circle, and then you have vertical cross section in this circle. So it's like cylindrical vortices, and these are like common vortices and so on. And they look pretty symmetric. So the red and the blue, if you saw the movie and it actually played, then you will see that the red and the blue overall are quite symmetric. But then when you go to the case in Berger number 25, where rotation effects become more important, then essentially what you have is you got some sort of asymmetry. And when Berger number is infinity, then you don't have so the asymmetry here is quite specific. So what happens is that if you saw the movie, you would see that in general you've got the cyclonic vortices which are in blending. The cyclonic vortices are much larger than the anticyclonic vortices, which are smaller. And that has to do with stability of vortices in rotating stratified world. So we are trying to look into that. And then once you go to Berger number infinity, then you again get to the symmetric pattern because the rotation effects are not important. Sometimes it just goes. Okay, so actually, here I want to sort of go to. Can I ask you to just wait? So just keep skipping slides. I don't want to do it. So keep going. Keep going. I just want to show the final. Keep going. Keep going. Yeah. So the slide that you missed were the result of something called spectral POD, where we are essentially using the fact that we've got certain discrete frequencies, shedding frequencies in there, and then we look at the unsteady data time series, and we extract the structure of those vortices that are being shed. That's a very nice way of isolating the vortex structure. And if you do that and then look at the movies and so on, what turns out that what's going on is that as you increase the effect of rotation going from here to there, then you basically go from this inclined vortices to straight vortices, vertical vortices. But interestingly, with all of this changes that we see in the size of the individual vortices, their shape and so on, inclination, the frequency does not change. And this is kind of an interesting thing. I think we are right because there's some experimental data that there's not much experimental data done at sufficiently high length numbers to see these unsteady vortices. But what is that does seem to indicate that Rossby number and Fluke number do not substantially affect the shedding frequency. And that's actually the papers from lawyers. And there are several questions for future work. And what we are particularly interested in right now is the instability circle from Sutanu case, Rossby number to the order 1 way. And so these two things are important, but not sure we look at it. I'm also interested in multi-scale topography. So if you have hills of different diameters, different aspect ratios, then how does that affect the flow? And we have the capabilities to do that. And since I did promise to Okay, I had a final slide, and I just wanted to, but I can just talk about it. So I did show some pictures about these underwater submersibles and so on. Right? So there you have weights which are very different. So there the food number is no longer less than order one. It's order one or much larger than order one. And then you might think that, hey, why do you care about stratification? Indeed, near the weight you don't, near the body you don't care about stratification. But what happens, and the reason, so we've had quite a few students working with me and evaluated on this several aspects of this problem, is that as the fluid develops, the vortices become larger, so then the time scale of the vortices, and also the weight effect velocity decreases upstream, right? So then the characteristic time scale of the vortices changes, it becomes larger and larger. So eventually you're pretty much guaranteed, if there is a weight and if there is stratification, eventually the picture changes from three-dimensional turbulent weight to whatever stratification goes to. And that distance downstream is order of fluid number. The fluid number is 50, then by 50 body nanometers. And for higher number weights, they're there. And you can see in the surface, you see the weights of ships and so on. They go on a plane, if you see, they go on and on and on. And so the similar thing for different reasons happens when you go for these submersibles that are going on. And so we've been looking at that particular problem and looking at how the body shape changes things, how stratification profiles changes the weight dynamics and so on. And with that, also. Sorry about the technical difficulties.
Yeah, sorry about that. Yeah, okay.
The frequency spectrum is like you had a frequency domain on the slide. So is this associated or is it due to this
Synchronization. Yeah.
Polaris frequency, or if you see the signatures of this Polaris frequency and the tidal frequency there, or there is something else?
So if we are basically seeing FT over 2. So the frequency was half. FT over 2 and FT over period, yeah. So that's period. So you are seeing that in the frequency spectrum. Precisely when I showed that there was. So I showed you a lot of qualitative pictures, right? But yeah, we did quantitative stuff, including spectrum.
So the other question is on when you start to rotate, usually in a non-stratified way, you see this Taylor curve. Is that similar to this where you have this with the increasing rotation, you get that stabilizing effect?
Yes, absolutely. And but there are some interesting things also because it's a finite Taylor column, right? And so these Taylor columns as they're moving, they ensure that they generate their own internal waves. So it's different from the infinite Taylor column.
So in simulation, right, depending on how long your downstream distance is in the model, so you should after separation knowledge, split and everything, you continue to see upscale cascade because you expect that entity like efficient, strong transportation guidelines, stratified turbulence, and you should continue to see the processes grow and size. Right? So if you have a number domain, you
yeah, I did not show this to you in this particular problem, but we have done so-called hybrid simulations, not for the hill wake, but you probably do in the future. But for this engineering wakes, we go to X equal to 100 diameters and so on. And then once it goes to the so-called quasi-2D, they will do vortices. And you get. But it's interesting because you still have dissipation because they're a three-dimensional structure. They're not homogeneous.
Another question is, so the dissipation that you see mainly after separation, what part of it is, I guess that on the anti-cyclonic side, a lot of the distribution due to centrifugal and symmetric instabilities. So have you looked at the potential quantity that CM?
We're discussing that, we're running it a little bit, yeah. So, yes, that's it, we do this, and there are some.
You also see paraffin instability in these situations. It's not long enough.
So we see the parabolic instability in our frontal problems. Yes. Right.
General question about what about the waves in the atmosphere?
Similar situation. Similar situation. So you have these, like the picture that I showed you from the cloud cover, right? So there were these volcanoes, and so that was exactly, these were these mountain waves, and you could see them from the cloud cover. In fact, these new vortices were first studied not in the ocean, but that you can see the atmosphere much easier than you can't really see the ocean. Yes. Yeah. In fact, these huge wind farms are kind of interesting because people have found that as the huge, especially in the if there's a stratified region, right? These huge wind farms, they can change the microclimate. They extract so much energy from the atmospheric winds, and the stratification is strong, right? If it's strong, then it changes dynamically the local winds. So these huge wind farms are really effective.
Any other questions? Okay, if not, we'll thank Sutanu again. This PA Bada
Thank you. You know.